Welcome to The Explainer. Today, we're going on a really fascinating journey to demystify exactly how machines find hidden patterns in messy, completely unlabeled data. I mean, imagine looking at a massive, chaotic scatterplot of information and trying to find the underlying structure without any sort of answer key to guide you. That's the magic of cluster analysis. And by the end of our time together today, you're going to understand the core techniques that make it all possible.
We've got a clear roadmap for this explainer. First, making sense of messy data. Second, the classic k-means approach. Third, embracing ambiguity with fuzzy clustering. Fourth, building trees with hierarchical clustering. And finally, number 5, tackling complex shapes with density.
All right, let's dive right into Section 1, Making Sense of Messy Data, the unsupervised learning problem. Let's define the exact problem we're trying to solve here.
So what exactly is cluster analysis? At its absolute core, we're looking for a collection of data objects that are highly similar to one another within the same group, but distinctly dissimilar to objects in other groups. We define cluster analysis as an unsupervised learning process. Now this is key. This means we're learning purely by observation. We don't have predefined classes, we don't have a teacher handing us examples to learn from. The data just has to speak for itself based entirely on its own internal characteristics.
Think about the fundamental difference between clustering and classification. When we do classification, we are squarely in the supervised realm. We have labels, we use clear class assignment rule, and we try to detect the boundaries among known categories. But in clustering, we're dealing with the wild west of completely unlabeled data. It is unsupervised. We are forced to identify structural properties and group points simply based on neighborhood criteria or density.
Before we get into the heavy math and the mechanisms, it's absolutely crucial to understand why this actually matters. These aren't just abstract academic concepts, right? These algorithms help biologists organize the taxonomy of living things. They help marketers segment customer bases to build highly targeted programs. City planners use them to group houses by type and value. Seismologists literally cluster earthquake epicenters to map out hidden continental faults. And meteorologists use them to find complex patterns in the ocean and atmosphere. I mean, it's literally everywhere.
Moving on to Section 2, the classic k-means approach, finding the center. Let's see how arguably the most famous partitional approach builds our baseline understanding of grouping data.
What's really cool about the k-means process is how visually simple it is. Imagine a spread of scattered data. We arbitrarily drop in some center points. We call those centroids. Then we assign every single data point to its nearest centroid. Once that's done, we calculate the actual mathematical center of that newly formed group, and we move the centroid to that exact new spot. It's this elegant, constantly updating process to try and capture the data's structure.
So the takeaway here is that k-means is essentially a looping 4-step procedure. You pick k, which is just the number of clusters you want. You compute the centroid or mean point for each partition, you assign the objects, and then you simply repeat and loop this process until there is absolutely no change in the assignments. Once those centroids stop moving around, your clusters are locked in.
But here's where we hit a bit of a wall. K-means works flawlessly on beautiful, distinct, well-separated groups of dots. It absolutely thrives there. But what happens when the real world gets messy? Think about chaotic, intertwined spirals of data. K-means relies on straight-line distance to a center point. It just cannot draw a circle around a spiral without accidentally grabbing a huge chunk of the neighboring spiral right along with it.
And this limitation serves as our perfect pivot. If simply finding a center point completely fails us on complex geometries, how on earth do we adapt our math to cluster this intertwined reality? We obviously need some different tools.
Which brings us to Section 3, Embracing Ambiguity with Fuzzy Clustering, Sharing Identity. To handle these more nuanced realities, we transition to an approach that frankly doesn't force strict boundaries. We call this probabilistic or fuzzy clustering.
Now, the rigorous objective function of a method like fuzzy c-means might look incredibly heavy on the math, but don't let the notation overwhelm you. Just focus on the intuition here. There's a specific variable that represents the degree of membership. It's an iterative optimization just like k-means, but with a massive philosophical twist.
So instead of a strict black and white you're in or you're out assignment, where a point is either in cluster A or cluster B, this method brilliantly allows a single piece of data to share its identity across multiple groups. A data point sitting right on the border of two clusters might be a 50% match for one and a 50% match for the other. It perfectly reflects the real world, where things very often belong in overlapping categories.
Next up on our agenda is Section 4,
building trees with hierarchical clustering, the bottom-up approach. We're going to look at a completely different strategy now that relies on building relationships from the ground up, rather than finding a center point or dealing with probabilities.
This strategy is called agglomerative clustering. Think of it as a bottom-up approach, literally building larger groups piece by piece. Initially, every single data point out there considers itself to be its very own independent cluster. Then, step by step, the algorithm finds the two clusters that have the least dissimilarity, so the ones that are closest together, and it merges them. It continues in this fashion until, eventually, every single node belongs to one giant unified cluster.
To build these groups, though, the algorithm has to decide exactly how to measure the distance between two clusters that contain multiple points. It uses different, what we call, linkage criteria. For instance, single linkage looks at the smallest distance between the closest neighbors in two different groups. Complete linkage? That looks at the largest distance, the furthest points. Average linkage takes the mean of all pairwise distances. And centroid linkage just measures the distance between the calculated centers of the groups. Each choice drastically changes the shape of your final clusters.
And the result of all this bottom-up merging is a beautifully complex structure called a dendrogram. Because we built the clusters level by level, we've essentially created a nested partitioning tree. What's amazing here is that to figure out the true number of clusters, we can literally chop this visual tree at whatever horizontal level we desire. Every connected component below our cut line becomes its own cluster. It gives us incredible visual control over the exact granularity of our data.
Finally, let's hit Section 5, tackling complex shapes with density, handling weird geometry. It's time to address the elephant in the room, those incredibly complex, non-linear spirals that completely broke the K-means algorithm earlier. To fix the spiral problem, we use connectivity and density functions. Density algorithms basically strictly categorize every single point in space into one of three distinct roles. First, we've got core points. These guys are deep in the thick of it, completely surrounded by other points. Then we have border points. They don't have quite enough immediate neighbors, but they're close enough to be reached by a core point. And finally, noise points, the outliers just sitting all alone out in the empty space.
This brilliantly illustrates the true power of density. The algorithm literally hops from core point to core point, building these long chains of density-reachable paths. This chain reaction of dense neighborhoods means the algorithm can naturally trace along a continuous, winding, nonlinear shape, just like our spiral. As long as the dots are densely packed next to one another, it just keeps following the trail, all while completely ignoring the empty space and completely tossing out those noise points. It maps the true, organic shape of the data.
Well, we've covered incredible ground today, from finding distinct centers with K-means to sharing identities with fuzzy logic, building bottom-up trees, and tracking dense neighborhoods to solve those really complex geometries. Now that you understand these powerful, unsupervised tools used to find order in complete chaos, I want you to think about your own field of work or study. What unseen relationships, what hidden patterns, and what complex shapes are just waiting to be discovered in your own messy data? Thanks for joining me on this explainer, and keep looking for those patterns.